This session will probably be pretty quick. Now, I've already let in quite a bit for this session from the earlier one, talking about the analogy to be made between the equivalence of computer programming languages, for example, like Fortran and C and Pascal and Lisp and so on. Whatever you can do in one language, you can do it in the other. They're equivalent in that sense. They have the same power in the sense they can all execute the same set of algorithms, if you like. They can do things, maybe with different levels of efficiency, of course. The latest supercomputers are getting up to 10 to the power 16 operations a second, so incredibly more efficient than a Turing machine. But in terms of power, in other words, what they can describe and execute and recognize and so on, same, right? And that's with computer languages. And similarly with models, mathematical models of computing devices, automata. The various automata, general purpose programmable computing models, Turing machine, lambda calculus, post machines, and so on. They're all equivalent. So for similar reasons. Okay, so. There are a lot of models, and they're all equivalent. You can prove, you just show the equivalence of one with the other with these corollaries. That we've already done three of these corollaries, showing three variants: the multi-tape, the non-deterministic variant, the enumerator variant. They're all equivalent to a standard single-tape Turing machine. Okay, so we've shown that, and it's widespread. There are many other models also equivalent to the standard Turing machine. So in that sense, the robustness of a Turing machine is, like I said in an earlier board, is truly amazing, like extraordinary. It's there's something deep going on there. All these models, they can simulate each other. Now, if you can do that. And that's how you prove equivalence usually, by having one model simulate the other. So common sense says, if one can simulate the other, then whatever the one can do, the other can do, because whatever the one is doing, the other one's simulating the same performance of the first one. Well, that means whatever the first one can do, well, obviously the second one can do, because the second one's capable of simulating the first one, right? So, sort of obvious. Okay. Now this equivalence, of all these general purpose programmable models, and paper models of all these machines, the equivalence of all this, it has philosophical consequences. That won't be clear for the moment, but we're leading into that. Okay. In fact, the ChurchTuringThesis is what we're heading towards, which is the title of the whole chapter. We still haven't got there yet. Won't be until towards the end, in fact. And we're getting close to the end of this chapter. All right. So you can imagine different kinds of computational models. Like probably the two most extreme different versions, I suppose, of computational models would be ones. On the one hand, let's say, it's debatable. One would be the Turing machine model, this sort of engineering, mechanical type focus on things, and the lambda calculus, which is manipulating lists effectively, the computer language Lisp, L-I-S-P, which is short, I think, for list programming or processing. L-I-S and the T's dropped, and then the P, Lisp. Okay, anyway. All these models, they can all they can all compute, they can all process, describe, recognize, whatever, the same class, the same set of, in this case, algorithms. They can all do the same jobs, effectively. And we're heading towards the definition of an algorithm. The definition of algorithm, yeah, that's the next section, in fact. Getting there soon. Okay. Now, each model has its own quirks, individual characteristics, its own arbitrariness, if you like. But the set of things that they can do, the class of algorithms that they can execute, seems to be sort of inherent. Sipser uses the word natural, which he defines that all these models, all these equivalent models, they can all execute the same class, the same set of algorithms. They all have the same power in that sense. Okay. Now this equivalence, if you like, it had quite an impact on mathematics, and we'll show that in the next section. That's, I think, 3 sections. Let me check. Three sections in this chapter. So we're about to get into the third and last one of the chapter, I think. Let me check. Yeah. So chapter 3, the ChurchTuringThesis, section 1, Turing machines. So talk about that at length. Section 2 was variants of Turing machines. So pretty well just finishing that now. And the third one is the definition of algorithm, which is the last and third section of the chapter 3, ChurchTuringThesis, which we still haven't spelled out what it is. Okay, so this, in other words, this awareness of the equivalence, equal power, of all these different models, that awareness in turn had a knock-on effect, a consequence, on it had an impact on mathematics. And I'll give you an example of that. Well, now pretty much. So we'll go to the next square. So a new section. So section 3, chapter 3, 3.3. So the definition of algorithm. Now, if you're a computer science guy and not a mathematician, and if you have not studied theory of computation before, you probably have an intuitive notion, idea of what an algorithm is, right? If you ask an intelligent, relatively informed person on the street, what's an algorithm? Somebody who's done some computer programming, let's say, and they'll probably tell you something like, oh, well, it's a kind of step-by-step method to arrive at some goal. It's sort of like a recipe for cooking. Do this first, then do this, then do this, then do this, to arrive at your final goal, to achieve some task. So it's like a step-by-step recipe, a set of instructions to achieve something. That's an algorithm, and that's probably a widely held, intuitive, somewhat vague definition of what an algorithm is. But for the mathematical logicians, that was too vague. They wanted a much more precise definition of what an algorithm was. And then, interesting, historically, that had consequences for mathematics. Making the definition of an algorithm precise had consequences for mathematics. It allowed, I'll jump ahead a little bit, give you a taste. It had the amazing consequence that you could actually prove mathematically that certain things were not solvable, that you could not make a decision. You could not, for example, accept or reject a certain string, that kind of thing. Which is pretty deep if you think about it. I mean, it's quite amazing. You actually prove that something is impossible to find an answer to, that can't be solved. You can actually prove that it cannot be solved. I mean, think about it. It's incredible. And Church was, I think, the first to do that, and then followed very quickly by Turing. With his famous halting problem, which we'll do fairly soon. It's the next chapter, so within a week or so, I guess we will have done it. So these kinds of proofs, these impossibility proofs, proving that some things can or cannot, and it's the cannot that's interesting, be computed. Certain things, certain questions cannot be computed. The proofs of that comes out is a consequence